So usually when I ask people how they feel about logarithms or what they know, their response is, what the heck is a logarithm? And even after learning about them and applying them and solving problems with them, a lot of people still don't really understand what they are. Which is a shame because we actually think about logarithms a lot even though we don't really realize it. Like, let's take a look at a really basic equation, right? So 2 to the third power equals 8. It's a very simple equation and it's pretty easy to understand. 2 to the third power just means 2 times 2 times 2, and of course that's 8. But now let's represent that visually, right? So this says 2 to the third power equals 8. And let's think about what this means as we just remove like one thing at a time. So like if I get rid of this 8, let's just call that some unknown. And then if I write the equation that this says, it would be 2 to the third power equals this unknown thing. And to figure out what that unknown thing is, we just have to perform this operation. We just have to do an exponent. So we've been doing that forever. So we know that 2 to the third is 8. Let's go back to knowing that this is 8 here. And let's get rid of this other number. Let's say we don't know what this 2 is here. So let's just call that some unknown. Now if I use this triangle again and just rewrite what this equation would be, it would say some unknown to the third power equals 8. So again, I want to figure out what this question mark is. I want to get it alone. But I know how to do that. To get rid of this third power, I just have to take the third root of both sides. So then I would have the question mark equals just the third root of 8. And I know how to do that. I just have to perform this operation. In this case, it's a radical. So again, we can go back to knowing that the third root of 8 is 2. But let's take a look at what happens if I get rid of this 3 at the top and replace that with an unknown. If I use this triangle to write an equation, I would have 2 to what power to this unknown exponent equals 8. Now this is a pretty obvious equation. 2 to the third power equals 8. But I could ask you something like 3 to what power equals 7, and that's a lot less obvious. So it's important to be able to figure out what this question mark is. And if I wanted to get it alone, you might be tempted to take like whatever that number is, like the question mark root of both sides. I know that sounds really weird, but at least these would go away and you'd be left with 2 equals this question mark root of 8. But that doesn't help me. That doesn't get me any closer to knowing what the question mark is. It doesn't get the question mark alone. So that's kind of a silly thing to do. And the fact is we don't have any other operation that would get that question mark alone. And so what this is called is a logarithm. And the way we'd write that, we would say we would take the log base 2 of both sides. So the log base 2 of 8. So there's a log property that says that these would cancel out. I mean, those are inverse operations, basically. And we would have that the question mark is alone, finally, and it would equal the log base 2 of 8. So now we just have to be able to evaluate these log expressions. So the way we say this is we'd say the log base 2 of 8. But when you're thinking about evaluating them, really what you're thinking is 2 to what power equals 8. So unfortunately, the way we write logarithms is pretty confusing. Like the way this is written, it certainly doesn't make you think to say 2 to what power equals 8, but that's what it means. So let's focus in on these two different forms of the same equation. The first one is in exponential form, and the second one is in logarithmic form. And it's a really important skill to be able to rewrite these equations in either form. And there's a couple little tricks that I remember to help me do that. One of the tricks that I remember is that the base in the exponential form is the same as the base in the log form. Another little phrase that I repeat to myself a lot is logs are exponents. And that's because if you look at a log equation, you could say like logs are exponents. And when I get to the number 3, I'm saying the word exponent. So in the exponential form, the exponent was the 3. So if you know where the bases go and you know where the exponents go, then it's pretty easy to fill out the rest. But one more trick is in log form, it's called around the world a lot of times because you start at the base, which makes sense, you always start at the base, and then go around the equation sign to the other side. And this is just like directions on how to rewrite it. So if you start with the base of 2, just like you have over here, and then you go around the world to the 3, that means so 2 to the third power, and then back again to the 8. So 2 to the third power equals 8, and it creates this circle kind of pattern. So now we kind of have a handle on how to switch between exponential and log form, and we saw what a log really is. Remember, the point of using a logarithm is so that the unknown thing in the exponent can come out of there and we can get rid of the base. So logs basically just undo a base. But now we have to go a little bit deeper. The goal here is to be able to solve logarithmic equations. So there's a couple of properties of logs that we have to learn about that will help us in that process. So there's a few basic log properties that we'll start with, and since I'm a lot more familiar with exponential form, I'm going to use what I know to rewrite these, and I'm going to use that around the world idea. So remember, if we start at the base, in this case it's a, so a to this unknown power equals 1. So I'm going to write a to this unknown power equals 1. And we know that anything to the 0 power equals 1. So log base a of 1 equals 0. So that's important because we're saying this base could be a, it could be anything. So that's saying that any log of 1 equals 0. Anytime you see that you're taking the log of 1, you know for a fact it's going to be 0 right away. Let's do that same thing for number 2. So a to this unknown power equals a. So I could write a to some unknown power equals a. And we know that anything to the first power is itself. Number 3 looks similar, but there's this exponent here, x. I'll do the same thing. So a to some power equals a to the x. So I could write a to some power equals a to the x. And if the bases are the same and we're saying these are equal, the question mark must be x. So that's a very roundabout way of just saying that when you have log base a of a, you can just cancel those and you're left with this exponent. And if you're wondering if we could do the same thing here with number 2, we can. The exponent on this a was just 1. So log base a of a cancels and you're left with that exponent. And I think the last one is pretty obvious. It's just saying that if you have the log base a of x and the log base a of y, and you say that they're equal, then x must be equal to y. In practice, that just means if you have a log term equal to another log term and the bases are the same, you can just cancel them and then work with what you're left with here. So like I said, those first 4 properties are pretty basic. These next 3 are what I'd really consider to be the log properties. This first one we would call a product to sum property because we're taking a product inside of a log term and we're changing it to a sum of 2 separate log terms. Or you can go backwards. If you're given 2 log terms added together, you can condense them into one single log term where you're multiplying the insides. Now, that seems like a weird thing to be able to do, just change it into one single log term. So let's try to make some sense of that. So I'll need some space here, and I'm going to try and use that triangle example and see if we can kind of capitalize on that. So let's take this. So 2 to the 3 plus 4, so 3 plus 4 would be 7, and 2 to the 7th power is 128. And I know that a different way of writing this would be 2 to the 3rd power times 2 to the 4th power equals 128. So now if I were to draw that on those triangles, I would have 2 to the 3 plus 4 power equals 128. And I could break that up into 2 smaller triangles, basically like what we're doing down there. So I'd have 2 to the 3rd power, which equals 8, and 2 to the 4th power, which equals 16. And remember before, this unknown stuff at the top of the triangle, that's where the log came from. So if you want to add these 2 logs together, that's the equivalent of multiplying these 2 things together, 8 times 16, because that's what we had here. This was 8 and this was 16. 8 times 16 is 128. That's the same thing as like just adding these 2 logs together. And that's because these are the same thing here. 8 times 16 is 128, and 3 plus 4 ended up on the top of the triangle over there. So this is all pretty abstract and not really how we do log problems in practice, but if you're really curious as to like why this works, that's why. Now, for the sake of time in this video, I'm not going to go through that same explanation for both of these other properties, but you could basically do the same thing with those triangles and reason through this. Also, if you think about subtracting exponents, that comes from dividing bases. That's why we have this quotient to difference property. So if you have 2 things inside a log being divided, you can break that up into 2 separate log terms that are being subtracted, or vice versa. You can take 2 separate log terms that are being subtracted and you can condense them into 1 log term by just dividing the inside stuff. So we had the product to sum property, the quotient to difference property, and the last one is the power property. This comes from, like, if you think of the exponential equivalent, if you have an exponent raised to another exponent, or like a power to a power, well, what do you do with those exponents? You multiply them, and that's what we're doing here. Visually, how I think of this is anytime you have something inside a log being raised to a power like that, you can just drag that power in front of the log, and it just becomes that coefficient. So let's finally look at some actual examples. It says use the properties of logarithms to expand the expression completely. So this first one here, we'd have just one log term, log base 5 of this stuff, 5 divided by x. Since that's a quotient, I'm going to break this up into 2 log terms. So I'm going to write log base 5 and log base 5. I know this is a quotient, which will change into a difference. So then I'm just going to take the top of the fraction, that'll go in the first log, and then I'll take the denominator, and that'll just go in the second log. So that says log base 5 of 5 minus log base 5 of x. Now that's expanded completely, but we can actually take this a little bit farther because this is just a bunch of numbers and I can evaluate that pretty easily Because remember, log base 5 of 5, that's like saying 5 to what power equals 5, and that's 1. So this says 1 minus log base 5 of x. Number 2 is a bit more complicated. We have one log term, log base 4, but then the stuff inside is 5 times the square root of x. So the first thing I notice is that product there. I'm going to break that product up by splitting this into the sum of two log terms. And they'll both be log base 4. I'll take the first thing, the 5, that'll go in the first log term, and the square root of x will go in the second log term. Now, I can also go farther with this because the square root, remember I could actually rewrite that as an exponent as like a 1/2. So this is log base 4 of 5 plus log base 4 of, I'm going to rewrite this as x to the 1/2 power. And the reason I'm going to do that is because now I have that power property where I can take that out in front of the log term. So this is actually log base 4 of 5 plus 1/2 log base 4 of x. The next two problems have us just working backwards. So they give us this expanded log expression and we have to condense it down into just a single logarithm. So for the first one, I see that I have one log term plus another log term. But actually, before I even condense that addition there, I see that this 2 could be brought up as an exponent on that x. That's like the power property just in reverse. So I'm going to rewrite this one as log base 3 of x squared plus, and then this will just stay log base 3 of this stuff, x plus 1. And there's nothing to do with this stuff inside the log. That's already inside, so that won't help me condense anything. But I will take these two log terms and condense that into a single log term. So log base 3, but now instead of adding these two logs, I'm going to take the inside stuff and multiply it together. And I'm going to use brackets here just to differentiate between the parentheses. So let's multiply x squared times x plus 1. And then maybe take that one step farther, so log base 3 of, and then I'm just going to distribute that x squared in. So this would be x cubed plus x squared. And that's as condensed as you can get. The next one's kind of a mess. There's a couple different log terms, and it says ln, that's natural log. Natural log is just shorthand for log base e. It's just e is such an important base and so frequently used, we don't want to have to write that all the time, so we just write natural log, or in this case ln. So first thing I notice in these brackets is I have two natural log terms that are being added. I could combine those into just a single log term, so natural log of, just multiplying the stuff inside. So this would be z times z plus 5. And this is still a mess here, and that's a lot of parentheses. So let's get rid of some of that. I don't need the parentheses in front between the 4 and the natural log, so I don't need these. And I could also distribute this z in here, so this would be 4 times the natural log of z squared plus 5z. Now at least that looks a little bit nicer. And actually I'm going to take that 4 in front and bring it up as the exponent. Meanwhile, I'll bring this negative down, but then I'm going to do the same thing with this 2. I'll bring that up as the exponent on these parentheses. So it would be the natural log of z minus 5 squared. Now I see that I have just two natural log terms, and they're being subtracted. So I can condense those into one natural log term by dividing the insides. So I condense that here. It's just one big natural log term now, and the stuff inside the natural log is being divided. So it's this top set of parentheses divided by this bottom set of parentheses. So we're finally at the point now where we can start solving these log equations. And there's a couple steps to think about that'll help us through these. So the first one here says isolate the log function and then rewrite it as an exponential function, because those are a lot easier for us to understand and work with. So like number 1 says 2 plus 3 times the log base 3 of x equals 8. And I know it kind of looks like this 2 plus 3 is together, but the 3 is the coefficient on the log terms. So I'm just going to get rid of that 2 by subtracting it from both sides. So then I'd have 3 log base 3 of x equals 6. And then I'll get rid of that 3 by dividing both sides by 3. So then I have log base 3 of x equals 2. And notice I didn't divide the base by that 3. That stayed the same. Log base 3 is the function. I just got rid of this 3 and then divided 6 by 3 and got 2. Now our log term is isolated, so we can finally do a round the world and rewrite it in exponential form. So 3 to the second power equals x. And of course that's 9. So that's the solution to this log equation. If you wanted to check your work, you could put 9 in up here, and then think about evaluating this log term. Log base 3 of 9 means 3 to what power equals 9? Well, that would be 2. So this stuff here is 2. So now I have 2 plus, okay, so 3 times 2, that's 6. and then 6 plus 2 is 8. So there we go, it works out. In number 2, the log term is already isolated. There's a bunch of stuff inside, but it's just one log term over there. So I'm going to rewrite it in exponential form right away. Remember, this natural log is just log base e. We just don't write the e. But if I thought about starting there and then doing around the world to rewrite this in exponential form, I would write e squared equals, and then the square root of x plus 2. Then I'd want to get rid of the square root by squaring both sides. And remember, a power to a power means you're just going to multiply them. So that's e to the 4th equals over here just x plus 2. So obviously subtract 2 from both sides, and x equals e to the 4th minus 2. That looks pretty simple, and if you wanted your answer to be exact, you could just leave it that way, or you could plug it into a calculator and get a decimal approximation of it. So I did that and I got 52.6 roughly. Another step they give us to think about when we're solving a log function is to condense multiple logs into one log function, and then you can rewrite it as an exponential. So looking at number 3 here, we've got log base 4 of x plus log base 4 of x minus 1. There's 2 log terms there, and they're being added. So we saw that sum to product property. I can change the sum into just one log term. So log base 4 of, and then I'm going to multiply the inside stuff. So x times x minus 1. And it might be a little bit confusing as to if just the x is inside the log or if it's all of this stuff. So you might want to write an extra set of like parentheses or brackets around the outside there. So anyways, I put these 2 log terms together into one log term, and this equals 1/2. Now I have just one log term by itself isolated, so I can rewrite it in exponential form. So 4 to the 1/2 power equals that stuff inside there. So 4 to the 1/2 power equals that stuff. So x times x minus 1. All right, well, 4 to the 1/2, that 1/2 is like a square root. So the square root of 4 is 2. Actually, the square root of 4 is plus or minus 2 equals, and then over here I've got x squared minus x. So this is kind of a strange thing that we have going on here, but if I get everything on one side, I'd have x squared minus x plus or minus 2 equals 0. So basically we have 2 different quadratic equations that we have to try to solve. And if I just do x squared minus x minus 2 equals 0, I know I can factor that into x minus 2 and x plus 1. So that's easy. And this tells me that x equals 2 and x equals negative 1 are 2 solutions that I have. And then if I look at x squared minus x plus 2 equals 0, and actually if I just graph it real quick to see if I have any solutions, it doesn't even cross the x-axis, so I know there's no x-intercepts, there's no solutions. So the only solutions I have to work with are these 2 here. We got to be careful though, because by definition we can only take the log of positive numbers. If you think about evaluating a log up here, you could think like 4 to what power equals this thing, and if you raise 4 to some power, you'll only ever get a positive number. So that means that the stuff inside the log, that can only be positive. But we just said that our x values are 2 and negative 1. If I took that negative 1 and plugged it in up here, that would be taking the log of a negative. So that negative 1 is actually an extraneous solution. But if you take the other solution of 2 and plug that in, that doesn't cause any issues. We're not taking the log of any negative numbers, so we're good. So our last example, number 4, has 2 log terms again on the same side. They're being subtracted, so I'm going to change that into just one log term, and then I'm going to divide their insides, so x plus 4 divided by x. You'll notice that none of these logs have any base written. This is called the common log. If there's no base written, we just assume that it's a 10 there. And just like with natural log, like e is such an important and frequently used base, 10 is also a really important base. So since it comes up so much, we just call this the common log and we just don't write the 10. But anyway, I combined these 2 log terms into just one. I still have equals log of x plus 2. Now I'm going to use that property where if you have the same log on both sides, you can just get rid of them and then just set their insides equal. So x plus 4 over x equals x plus 2. Now I need to get this x out of the denominator so I can go about solving this. So I'm just going to multiply both sides by x, just being careful on the right side because I'm going to put that in parentheses. So these go away and I have x plus 4 equals x squared plus 2x. I can get all that on the right side. I would have x squared, so I'd have to subtract this x. That would give me just 1x, and then subtract 4, so minus 4. Now this isn't factorable, but I know this is a parabola that would open up, and it has a y-intercept of negative 4, so it must cross the x-axis somewhere. So I'm actually going to do completing the square with this. So I'll move the negative 4 back over to the other side. Actually, I'm going to rewrite this a little bit, so it would be x squared plus x equals 4. I added that 4 over. And then remember, you rewrite this as x plus 1/2. You take half of that b value down there. Squared equals, but now I have to square this and add it to both sides. So 1/2 squared is 1/4. And if I added 1/4 over here, that would just be 4.25. Now I'd have to take the square root of both sides to get rid of that squared. So I'd have x plus 1/2 equals plus or minus the square root of 4.25. And actually I'm going to change that 1/2 into a 0.5 since we have decimals on the right side anyways. And then just subtract that 0.5. So x equals plus or minus the square root of 4.25 minus 0.5. Now there's two potential solutions here. There's the positive version of the square root of 4.25 and the negative version. But if you think of taking the negative version of that and then subtracting 0.5, that's going to be a negative number. And back up here, I can't take the log of a negative. So I know there's only one possibility. So that'd be x equals the positive square root of 4.25 minus 0.5. And at this point, I might as well just type that into my calculator. And you get about 1.56.